Chapter 14, Chemical Kinetics. Kinetics is defined as the study of how fast chemical reactions occur. Some reactions are amazingly fast, really instantaneous, like when you bring a match to gasoline or place a piece of sodium in water, and other reaction rates are very, very slow, such as the rusting of an iron nail. This chapter will help us study and work with some calculations related to chemical reaction rates. Here's an overview of this chapter. Today we'll start with what a reaction rate is and how you measure how fast a reaction is occurring. We'll also learn to write rate laws that show us how the rate depends on amounts or concentrations of reactants. Later in the chapter, we will use the integrated forms of rate laws to see how much of a material is left at a certain time in the reaction, or given a certain point in the reaction after, let's say, 3 minutes or 2 hours or 30 seconds, what would the concentration of the material actually be? We'll also discuss a little bit about radioactive materials and their half-lives and how they can be used to determine the age of a sample. 14.1 is a quick recap of things we've learned in other science classes, factors that affect reaction rates. The 4 factors are concentration of reactants, temperature, catalysts, and surface area. Now, the first one, concentrations of reactants, is very useful to consider when you have an aqueous solution. However, sometimes we are going to be studying reaction rates with gases, and you should also know that when we work with gases, sometimes rather than concentrations, we may measure the amount of reactant that's present for a gas in terms of its pressure. So instead of measuring molarity, we may use torr or atmosphere or millimeters of mercury. 3 out of the 4 of these factors really come down to something called collision theory. And that's the idea that in order to react, particles have to collide and collide with enough energy to break those bonds. So certainly increasing our concentration means that we will have more particles present to collide in the first place. Temperature can play a role because as the temperature goes up, the particles have more kinetic energy and therefore would be more likely to collide. And then something like surface area provides more sites for those reactants to actually interact with each other. So if I think about sugar, doing a reaction with sugar, I could consider sugar cubes versus granulated sugar versus powdered sugar. And the powdered sugar would be likely to have the fastest reaction rate since there would be more contact with that sugar with whatever the other reactant might be. So that's a quick recap of things we've probably talked about in other science courses. For the new material today, section 14.2, we're going to talk about how to determine reaction rates, in other words, the speed of the reaction. And I'd like you to consider this series of images. In the first container, at time 0, we see there are all red molecules or atoms. After 20 seconds have passed, some of the red ones have been converted into blue, and after 40 seconds, we see the concentration of blue has gone up even more, and the amount of red materials or atoms has decreased. So when we talk about the rate of reaction, we can determine that by monitoring the change in concentration of either the reactants or the products as a function of time. So in this series of images, you can think about how fast are the red molecules appearing, or disappearing, or you could think about how fast are the blue molecules appearing. So you can view it either from the appearance of a product or the disappearance of a reactant. Now, to determine for this reaction, the red to blue spheres, we'll just call this reaction A to B. We can figure out the average rate as the change in concentration of A with respect to time, or change in concentration of A over change in time. And these square brackets indicate molarity if we're talking about an aqueous solution, and even sometimes when we're talking about gases it means the same, but it can also mean pressure. So sometimes instead of molarity we may see moles or torr or atmospheres or other units as well. Now this presence of this negative sign can sometimes be a source of frustration for students. And we'll talk about when that should be there and when it shouldn't be there. But I encourage you not to focus too much on that sign, but rather just how you get the change in concentration of A versus time. And if you're getting that part right, the sign will usually work itself out. Let's look at an example. So for this reaction that starts with C4H9Cl, we can see that we have its concentration over the course of the reaction with respect to time. And if we wanted to determine the average rate for these different time intervals, we could consider, for example, the average rate from 0 to 50 seconds, or the average rate from 150 to 200 seconds. And to do that, if I was doing this first interval, I would take the second concentration, 0.0905, minus 0.1. That would be my change in concentration, and then I would divide that by 50 seconds. And if you follow along with me and do that on your calculator, you should get 1.9 times 10 to the negative 4th. Actually, it probably has a negative sign in front of it. But because of this negative sign here, we would actually make that a positive number. And so what we're measuring is how fast this C4H9Cl is disappearing. And if you did that for each time interval, you would get the following numbers. Feel free to check a few with your calculator to convince yourself that those are actually correct. What I want you to notice over time, and in class we had different rows of students calculate these different values, we see that the average rate decreases as the reaction proceeds. In other words, the reaction rate will be very fast in the beginning, but then it will start to slow down. And if we go back again to the idea that concentration plays a role in reaction rate, and the more concentrated it is, the faster it will go, it makes sense that as this concentration drops, there will be fewer and fewer molecules to collide and react, and so our reaction rate should drop. Now, what we would have just determined is something called average rate. It's the rate over a span of time. And a way to think about it, if I were to drive to Minneapolis and it took me a half an hour, I might say my average speed was 50 miles an hour. Now, that does not mean that as soon as I jump in my car and start and put my car into drive, I'm not instantly going at 50 miles an hour and that is the speed I have for the whole trip. It's just my average speed. Maybe in the beginning while I'm in Delano, hopefully I'm driving like 30 miles an hour, which is the speed limit. Maybe when I'm outside of Delano and I'm out on Highway 12, maybe I drive faster than that. Keep in mind the average rate is for a span of time. Sometimes, instead of average rate, we want to determine instantaneous rate. And just like the name implies, the instantaneous rate is the rate at an instant, at a certain point in time. In order to determine that, we need to complete a graph, and that graph would be a plot of concentration versus time, and it would look something like this. And you can see that in the beginning, the slope of that curve is fairly steep, and as time goes on, as we go down along the curve, it does gradually slow down and kind of flattens out a little bit. And if we want to determine, what is the rate at any instant in time, what we do is you can see there are several tangent lines drawn to our curve here. And if we can determine the slope of a line that's tangent to the curve at any point, we would define that as the instantaneous rate at that time. So right here at 600 seconds, that tangent line is touching, well, not the way I've drawn it anyway, but a tangent line would touch that curve at exactly 1 point. And then we can determine the slope of that line. And that slope would be equal to the instantaneous rate. And clearly, again, looking from the graph, in the beginning, our instantaneous rate would be higher. This is a steeper line than it is down at the bottom. Now, this isn't something that Dr. Hansen's going to expect you to be able to do on a test. You're not actually going to have to make a graph, draw a tangent line to determine instantaneous rate, but you certainly should know the process that would be used and be able to describe that as a possible method. And we've already talked about concentration rates slowing down due to the concentration being less. So let's take a look at one of the examples that you're provided. Consider the following data. What is the average rate for the time period 150 to 200 seconds? So we're talking about this span of time right here. So if we do average rate will be change in concentration over change in time. And so we would have 0.0671 molar minus 0.0741 molar. And that occurred in a span of 50 seconds. And so if we do that on your calculator and divide, .0671 minus 0.0741 divided by 50. And then we get rid of the negative sign. The average rate would be 1.4 times 10 to the negative fourth molarity per seconds. My computer's going crazy here. Now, as you take a look at that answer, and I want to comment just on the sign, you can say since this A concentration is decreasing, this reactant must be disappearing. It's going away. So the average rate, I mean, that's the tricky thing about this sign. The average rate is either negative, or you could say the rate of disappearance of A, and then you would say a positive value. It's almost like being in a language arts class where they don't want you to have a double negative, because if you say you can't not do something, well, that means you actually can do it. So here, we would not want to say the rate of disappearance of something is negative. Instead, we would say the average rate is negative, or we would say the rate of appearance and then make it a positive number. Again, at this stage of the game, try not to focus too much on signs, but instead about getting the number correct. So this would be your answer for letter A. B, describe how you could use a graphical approach to determine the instantaneous rate at 425 seconds. So as we described earlier, you would want to plot a graph and plot concentration versus time, and then draw your curve representing how concentration changes with time. Draw a tangent to that curve at 425 seconds, and then the slope of that line would equal the instantaneous rate. So that's how you would do it. We do work with average rates a lot more than instantaneous rates. So we're going to cover one additional topic with average rates, and that is how stoichiometry or your mole-to-mole ratios play a role in reaction rates. We're going to start with a generic reaction and talk about how the rates of disappearance and appearance are related for each material. So if I have a generic reaction, A plus B yields C plus D. The uppercase A's and B's and C's and D's, those are the actual materials. They may be hydrogen or oxygen or water. The lowercase letters A, B, C, and D are the coefficients. So this reaction might read, 2 magnesium plus 2 hydrochloric acid or something like that. So imagine really you have coefficients and formulas in the places of the A's and B's. So as we describe how these rates of disappearance and appearance are related, we really have to focus on the coefficients that are in front of everything. And here is a way to set all the reaction rates equal to each other. Now at first this looks really kind of complicated, but if you take a look at them, each of them has some common symbols and usages here. We have change in concentration of A with change in time, change in concentration of B over change in time, change in concentration of C over time, and same thing with D. Now what's out in front of those is a fraction that's related to these coefficients. So since this coefficient in front of A was a little a, I'm going to turn that into a fraction. So if this was like 2a, this would become negative 1/2. If this was 3b, this would be negative 1/3. I want you to notice that the two on the left, the A and the B, have negative signs in front of them because they are reactants. They will be disappearing over the course of the reaction, and so their rates are negative. If you look on the other side at the products C and D, they are going to be forming during the course of the reaction, and so their average rates are a positive number. Now that's with A's and B's. I think it'll make a little more sense if we instead look at an actual chemical reaction. So here's another example from your handout. For the following reaction, indicate how the rate of disappearance of reactants is related to the formation of the products. So I'm going to take this equation at the top and kind of say how all the rates compare to each other. Now we know KClO3 is going away, so that's a reactant that's going to disappear, so it should have a negative average rate. So I would say negative 1/2 change in concentration of KClO3 over change in time would be equal to positive 1/2 change in concentration of KCl over change in time equals positive 1/3 change in concentration of oxygen over change in time. And at first, kids get really hung up on the numbers involved, but if you think about the coefficients, 2 to 2 to 3 ratio, the coefficient for KClO3 is 2, and KCl is 2, and oxygen is 3, a 2 to 2 to 3 ratio. And so if you think about how fast or slow these materials might either disappear or appear, you should see, since there's a 2 in front of potassium chlorate and potassium chloride, that the KCl on the right-hand side is going to appear at the same rate that the KClO3 is going to disappear, because they have both coefficients of 2. The oxygen, on the other hand, should appear faster because every time this reaction proceeds, 3 moles of oxygen are produced. So a good way to kind of think of it is to look at the coefficients, and the bigger the coefficient, the faster that material will either disappear or appear, depending on what side it's on, and the smaller the coefficient in front of the formula, the slower it will disappear or appear. So let's see if that makes sense with what we get as an answer for this second question. So it says, for this reaction, if KClO3 is being consumed at a rate of 3.9 moles per second, how fast is oxygen being produced? So I'm actually going to take the pieces out of I've set all these rates equal to each other. I'm going to take the pieces out of there that I actually need for this problem. So I'm dealing with KClO3 and oxygen. So I know negative 1/2 change in concentration of KClO3 over time is equal to 1/3 change in concentration of oxygen over time. I've left the KCl out because I'm not using that in this problem at all. Now, when I want to solve for how fast is oxygen being produced, I'm really talking about this part by itself. So I have to get rid of this 1/3 and move it to the opposite side. So if I just rearrange, I would have negative 3/2 change in concentration of KClO3 over time equals change in concentration of oxygen over change in time. Now I know in the problem it says that KClO3 is being consumed at a rate of 3.9 moles per second. So I'm going to substitute here. Oops. Now being consumed means it's going away, so its rate is negative. So I'm going to put in negative 3.9 moles per second. And I should get an answer of 5.9 moles per second. And if we think about what we were saying about the coefficients, the fact that oxygen has a larger coefficient than KClO3, that means it should appear at a faster rate than the rate at which KClO3 disappears. And since KClO3 was 3.9 moles per second and oxygen is 5.9 moles per second, that kind of supports the idea of looking at the coefficients. Let's look at one additional problem like this to kind of make sure this is all making sense. So it says for some reaction, 2A yields 2B plus C. And the concentration of A drops from 0.01 molar to 0.0045 molar in 50 seconds. Our first question, what is the average rate of disappearance of A? So change in concentration of A over change in time. So A is, we always do final minus initial, so 0.00450 molar minus 0.0100 molar, and that's in a span of 50 seconds. So if I subtract and divide, I should get 1.1 times 10 to the negative fourth molarity per second. And remember, it's a rate of disappearance, so I don't want that to have a negative sign. So that's how fast A is going away. If they had asked, well, they ask about C, so let's focus on that. So if I want to look at how A and C are related, we know that negative 1/2 change in concentration of A over time equals, there isn't a coefficient there, so I don't need a fraction. We have change in concentration of C over change in time. So luckily this one is already solved for change in concentration of C with regards to time. And it's going to equal 1/2 of what the change in concentration of A is with respect to time. So if I just take and substitute in, and this is a rate of disappearance. So technically if I wanted to put a negative sign on that, I could. I should get 5.5 times 10 to the negative fifth molarities per second. Now, again, you can use this mathematical approach, or you can kind of use some common sense, look at the coefficients as well, because in this reaction, we have 2A being consumed, and every time that happens, we get 1 C that's formed. So it's a 2-to-1 ratio. So A should be twice the rate of C, or you can think of it the way we did it in this problem, where C is 1/2 of the rate of disappearance of A. And so, again, signs, not a huge deal. Try to, make sense of those, but really we want to understand how we are coming up with these two rates. Our last section for today, 14.3, is concentration and rate. And we've spent some time talking about average rates and instantaneous rates and how stoichiometry plays a role. But we also want to know, well, how does the concentration of chemicals we use, how does that impact how fast or slow a reaction may occur? And to understand that, we need to be able to write something called a rate law. A rate law is an equation that gives the rate as a function of reactant concentrations. And I would make sure you understand, we only look at reactant concentrations, not products. And when we write rate laws, they are unique to each reaction. So a very fast reaction would have a different rate law than a very slow reaction. And we're going to start again with a generic approach and then move to specific. So if we have a general reaction, A plus B is reacting to form C plus D. In general, now that is not a, all right, sorry about that. The form of the rate law is always rate equals K. Then we see those square brackets again, which for solutions can be molarity, and for gases could be molarity or something like torr or atmospheres. Rate equals K times concentration of A raised to some power X and concentration of B raised to some power Y. And I want you to notice there's no C's or D's present in that rate law. It's always based off of concentrations of the reactants. X and Y, those exponents that you see, are called reaction orders. Those are determined by examining experimental data. So some of the problems we're going to be looking at, you will be given different trials or experiments, and they'll have a bunch of concentration data and rate data, and then we will use those to determine X and Y. The overall order is determined by taking X and Y and adding them together. So if X was 1 and Y was 1, then your overall order would be 2, second order. If, on the other hand, X was 1 and Y was 0, then it would be first order overall. So you just add them together. K, lowercase k, is the rate constant. And when we say constant, we kind of mean that in a relative sense. It's a little bit unlike, like the speed of light, which is a universal constant, and everybody would state that as 3 times 10 to the 8th meters per second. But instead, this rate constant, it would be, we would say, unique to each reaction and set of temperature conditions. So if you're talking about a different reaction, you're talking about a different value of K. If your temperature changes, you'll also have a different value of K. So let me walk you through an example of how to determine the rate law, and then we're probably going to add a few things to write down about first, second, and zero order reactions. So if I attempt for this given information to determine the rate law, I'm just going to start with like the generic rate law form. And we would say rate equals K, and then whatever my two reactants are. So it's going to be concentration of NH4 plus raised to some power, and concentration of NO2 minus raised to some power. Notice we do not write the products at all. Now, in order to determine X and Y, the orders of the reactants, I really need to figure out and isolate and compare some experiments where one concentration is changing, but the other is not. Let me give you an example. Let's say, and I happen to get migraine headaches a lot. Let's say that I go home and I have a terrible migraine headache. And I take some Excedrin migraine medication, but I also read online that grape juice is a great natural, alternative medicine health remedy for migraine headaches. And I go home and I take both Excedrin migraine and I drink grape juice, and wonderfully my migraine goes away. I have no way of knowing which of those two variables, the migraine medication or the grape juice, which one actually impacted my migraine or caused my migraine to go away. So when you look at these experimental data tables, make sure you are looking at experiments where only one of the two reactants is changing. And what I observe, I'm just going to split this data table in half. I notice in the first 4 experiment numbers that the concentration of ammonium, NH4, is changing, but the concentration of the other one is not. So that's really not having impact on my rate because it's not changing. So I can use information from trials 1 through 4 to figure out the exponent or the order for NH4. I like to work with nice easy numbers, and I see if I compare experiment 1 and 2 that the concentration doubles. I also notice that the observed rate doubles. So those are both changing by the same factor. And so I know that X is going to have a value of 1. So when we say something is first order, this is a good thing to put in your notes. For something to be considered first order, we would say that the concentration and rate change by the same factor. So for example, let's say the concentration doubles, and that causes the rate to double. Or let's say instead of the first and second trial, let's say I compared the first and the third trial. In this case, I see the concentration is 4 times as much, goes from 0.01 to 0.04, and the rate also is 4 times as much. And so whenever something is first order, both the concentration and the rate are impacted by the same factor. They both double, they both quadruple, they both are half as much, they both are, 3 times as much. Whatever factor applies to one applies to the other. That's first order. If we were to see something that was a second order reactant, a good example of that would be, let's say the concentration doubles and the rate increases by 4 times as much, because doubling is a factor of 2 and 2 squared is 4. Or if the concentration triples, 3 times as much, 3 squared is 9, so then the rate would increase by a factor of 9. There is one other type of order you may come across, and that is zero order. And in a zero order, for a zero order reactant, changing the concentration has no impact on rate. And so you could double the concentration or quadruple the concentration or cut it in half. Whatever you do to the concentration, the rate stays exactly the same. Okay, so that's a little bit of information on first, second, and zero orders. And I really don't think you'll see anything beyond that. Now, we said a moment ago that we thought X was going to be first order. Excuse me, yeah, NH4 would be first order, that X would be 1. We did not finish with Y. I'm just going to see if I can change colors here, make this a little easier to see. So to determine the order for Y, which is the order for NO2, I want to consider experiments where NO2 is changing, but the other one is not, so that it doesn't have any impact on my rate. Now if I compared, let's say, trial 5 and 7, from going from 0.0202 molar to 0.0606 molar, that's increasing by a factor of 3. And if you compare the rates, the rate is also increasing by a factor of 3. And so if the factor of increase or decrease is the same for both concentration and rate, that is another first order reaction. And so for this very full slide here, our rate law would be rate equals K NH4, and you wouldn't write the 1, we just understand it to be 1, times concentration of nitrite, NO2 minus. And since the exponent or order for NH4 is 1, and the order for Y is 1, then we would say overall, this reaction is a second order reaction. What I'd like you to do is try the last example on your handout and see if you can answer letters A and B. So we have the following data collected for the reaction, and you're supposed to determine the rate law and the overall order. So you should pause the video, give that a shot, and then finish the rest to see if you were correct. So hopefully you've had a chance to take a look at this one. Our two reactants are BF3 and NH3, and so my generic form of my rate law should be rate equals K. Oops. Go back. Sorry about that. As I was saying, rate would equal K times concentration of BF3 raised to some power or order times the concentration of NH3 raised to some order. Oh my goodness. Okay, my computer just went crazy, so I hope we're still kind of in the same place. I had to restart my recording. So, we are trying to determine the orders X and Y. And so, splitting my data table in half, I would use the trials 1 and 2 to figure out the order for NH3 and ignore BF3 for that one. And comparing trial 2 to 1, I see the concentration doubles and the rate doubles. So that means NH3 is first order. I would look at trials 3, 4, and 5 to determine the order for BF3, and I'd probably look at 5 compared to 4 and seeing that the concentration doubles and the rate doubles, it is also going to be first order. So our rate law, X and Y, would just be 1. I don't know if I'd get rid of that X and Y anymore. And so our rate law would be K times BF3 times NH3. And our overall order of the reaction would be second. 1 plus 1 is 2. What is the value of K to answer letter C? You can pick any one of these 5 trials to determine the K value, and I actually would encourage you to try more than one to prove to yourself that they are the same. But if I take and I solve for K, K would equal rate divided by concentration of BF3 times concentration of NH3. And plugging in, let's say, experiment 1, I would get 0.2130 molarity per second over, let's see, BF3 is 0.250 molar, and NH3 is 0.250 molar. And crunching that out on your calculator, let's see here, I should get 3.408 or 3.41. Now, this molarity will cancel out one of the 2 molarities, but I should have 1 over molarity times seconds, which sometimes is written as molarity minus 1, seconds minus 1. So that is the value of my rate constant. And then truly, the last portion, letter D, is probably the most useful part of having a rate law, in which case we can give you 2 random concentrations and ask you to determine the rate for those concentrations. And so letter D, rate equals, I'm going to put in my rate constant, 3.41, 1 over molarity seconds, times, let's see, we have a BF concentration of 0.05 molar and an NH3 concentration of 1 molar. And so if we multiply 3.1, we get 0.01705. And molarity, one of them would cross out, which means we get molarity per second, which is very appropriate for a rate. Now just one closing note. If, let's say, X had worked out to be second order, then as you plug in values, if the reactant happens to be second order, then you would have to make sure and square that concentration. In this particular reaction, it was first, but if it were to be second, then you would have to apply that 2 at that spot. That's it on rate laws. Certainly probably a foreign and different concept. Take a look at it. Please see me if you have questions, and have a good evening.